Here I'm talking about voltage or electric potential. Now, electric potential has some analogies to potential energy. In fact, you can use electric potential, which is usually notated delta V. Electric potential is kind of like height for potential energy. In fact, if you multiply height in potential energy by mass and gravity, you get out potential energy. And that is the potential for something to fall. Electric potential acts just like height in potential energy. If you multiply your electric potential times a charge, you get the potential for that charge to fall from one potential to another. Just like you'd have the potential for this mass to fall from one height to another. And sometimes we call electric potential voltage. It's kind of the engineering word for it. But electric potential and voltage I'll use as synonyms. In fact, when we measure electric potential, the unit for it is volts, V. So the symbol for this thing and its units are the same. It's going to be a little confusing maybe, but basically the symbol is delta V and the units for it are V, volts. And again, if you multiply charge times electric potential, you get potential energy. Now this can be used just like any other energy. It can turn into other forms of energy. It can turn into kinetic. It can turn into thermal energy. In fact, we'll see some examples tonight where you're asked to find the speed of something when its electric potential energy changes into kinetic energy. So basically you're just learning another kind of potential energy. We used to have gravitational and spring. Now we've got electric potential energy, PEE. Now there are some kind of rules for electric potential. Positive charges will fall from high to low potential. So they will go from high to low potential. That means that electric field lines point from high to low potential, because a positive charge will move like in the direction of the electric fields. So memorize this real fast. Positive charges fall from high to low potential. Negative charges will do the opposite. Negative charges will fall from low to high potential. So a negative charge would move from, say, negative 10 volts to 10 volts. Stays the same with rules for field lines. So we decided the field line pointed this way in the positive example. The negative charge will move opposite the field line, and it will go from low to high potential. If you need to pause the video to kind of wrap your brain around that, make sure you know these two facts from this slide. Let's look at an example of how we can use this. What is the potential energy if an electron, I should say is released between two plates with a 50 volt difference? So first I'm asked to find the potential energy. So I will call upon the formula for electric potential energy, PE equals Q delta V. Alright, well this is an electron, so its charge is going to be 1.6 times 10 to the negative 19th coulombs. And the change in potential, change is a difference between two things, and from 0 to 50 is 50 volts. So the change in potential is 50 volts. Then I multiply those two numbers together. And 50 times 1.6 should be 80. So 80 times 10 to the negative 19th, or 8.0 times 10 to the negative 18th joules. Now I'm going to take a second and confirm the math. I did some of that mentally, so maybe take a second and think through that. But this is our electric potential energy, right there. So that's part one done. Next, the problem says, what is the kinetic energy of the electron when it reaches the 50 volt plate? Well, since energy is conserved, and we're going to go ahead and assume, the problem doesn't say, but since it says released, I think we can safely assume that the thing is not moving here, so velocity, not voltage, velocity would be 0 meters per second. So it had no kinetic energy, only potential. Your total energy can't change, so all of this potential turns into kinetic. So the kinetic energy, and maybe we should be specific, at 50 volts is 8.0 times 10 to the negative 18th joules. Check. What is the speed of the electron when it reaches the 50 volt plate? Okay, so this is its kinetic energy. I just need to find its speed. So let's refer back to the kinetic energy equation. Ke equals 1/2 mv squared. This is going to get messy since I'm dealing with some scientific notation. This is certainly a time when I should solve for the variable first. So let's solve this equation for v. First I'll multiply by 2 and I get 2 Ke equals mv squared. Divide by m and then take the square root, and we've got 2 Ke over m. Square root of that is equal to v. Alright, so I'm going to need to know the mass of an electron. Go back in those handy-dandy notes Mr. Melvin told me to take. Alright, bring this equation up here. V equals the square root of 2 times the kinetic energy, which we just found, 8.0 times 10 to the negative 18th joules, over mass, which for an electron is 9.11 times 10 to the negative 31 kilograms. And let's do out that math. I'm going to grab a calculator. When I do that math, I get V equals 4.2, and I'm rounding, times 10 to the, see, decimal places, 1, 2, 3, 4, 5, 6, times 10 to the 6 meters per second. And handy physics fact, that's about 1/50th of the speed of light. Speed of light is 3 times 10 to the 8th meters per second, so it's about 1/50th the speed of light. So that's some ways you can use potential energy. So it is a fairly simple equation, but then you can use it in all the ways you could use gravitational or spring potential energy. So lots of complicated uses out of this new just simple formula. So if you remember energy conservation problems from last semester, no problem. You just got to memorize this new equation basically. If not, this is good review. All right, another example of how we can use this. How much work is done moving a particle with 3 millicoulombs of charge from A, which has 20 volts of electric potential, to B, which has 62 volts of electric potential. Remember, you got to think about electric potential like height. So the only thing complicated here is you have to remember that work is a change in energy, and we've talked about the work kinetic energy theorem, where work is a change in your kinetic energy. More generally, if you add energy or take away energy to a system, something has done work. So when it asks for how much work is done, it's actually just saying, well, what's the change in potential? Because whoever took this charge and moved it over here had to use that much energy or take away that much energy, so either had to put in that much energy to the system or take that much energy out of the system to move that charge. So this problem, once you realize that, reduces to work equals the change in potential energy, which simply equals Q delta V. So the problem tells us everything we need to know. We're just doing basically work equals Q delta V by the argument I provided down here. So now let's put in 3 millicoulombs. Now milli is 10 to the negative third, or moving the decimal 3 to the left. But it's been a scientific notation heavy unit, so why change now? 3 times 10 to the negative third coulombs. And a potential difference, so delta V would be the difference between 20 volts and 62 volts. Our final is higher than our initial, so change, by the way, is always final minus initial. So if we went from 62 to 20, we'd have a negative change. Since we're going from 20 to 62, we have a positive change. Remember, it's always final minus initial. So my final 62 minus my initial is 20. This matters why I'm saying this, because with an electron, you may sometimes have a negative. You can also have it happen with a positive, but more commonly with a negative. An electron will want to fall opposite the potential, so it wants to go from low to high potential. So you can see how negatives come into play there. Also, if you drag a proton the way it doesn't want to go, negatives can come into play there as well. Anyway, simple version of remembering all that is just to do final minus initial. So 62 minus 20 is 40 volts. And now we just multiply it out. And I get the work done was 0.12 joules. There we go. That's how you can use work and electric potential energy. Finally, some problems may ask you to find an electric field if you know potential and the distance between two plates, or the distance that a charge might travel. So if we say a charge travels from here to here and we know the electric field, find the potential difference. Also, there are things that you're going to see a lot of in the problems tomorrow called parallel plate capacitors. It's where two sides of a plate are connected to a battery. By the way, this is a symbol for battery. Get into that as we go. But anyway, two sides of a plate are connected to a battery, and that creates an electric field. It's an electric field in the plate. And you might be asked to find what's the potential difference between the two sides of the plate. Or you might be given the potential difference and asked to find the electric field. The equation that relates them is the electric field is simply the voltage divided by distance. So E equals potential divided by the distance. You could also easily get out of that potential difference. Potential difference is electric field times distance. I'm not going to show you examples there. It's a fairly simple equation, and the uses of it don't get very complicated. You're just given one and asked to find the other. So you need to know that, have that in your notes tomorrow. Some questions will come up, but it's fairly simple. You can find electric field given potential, or you can find potential given electric field. All right, that's it. See you tomorrow.